Well, it looks like we can begin. Today looks like it's going to be an empty class, but to folks who are watching this video later on, we'll still go over the announcements as usual. It's always kind of weird doing an empty class, but we all get used to it. We'll get through it. So the announcements for the day are our second exam is going to be next Monday. And I sent everyone individually instructions on Tuesday, which you can find here, on how to schedule your exam at the testing center. Really the same exact process for what you did on exam one that everyone got through. So get that signed up as soon as possible for booking your exam. And we won't have class officially on that day on Monday. The second exam covers these sections in particular, only up to section 3.7, which is part of what's due today. If you're a little bit behind on any one of those sections, I'll still take them late for full credit. And like we mentioned on exam one, really the first thing you should do to study for this exam to be prepared is just get caught up with the homework. I'll be grading them as soon as I get them to give you good feedback on each of those problems. Since we don't have a review, tomorrow we're going to be moving forward into finishing sections 310 through 11. No review for exam two means what I try to do when I write the exams is to make it quite similar to the problems that you actually solve in the homework and that we actually solve in the lecture notes. But you can also look into additional problems, the sample exam two problems down below here, for just extra practice. Well, that's the wrap up of the announcements. We're now on example 2 in section 3.9 with related rates. We have 3 examples left to get through on these. They're a little bit more challenging, so we'll kind of take our time with them. And getting through section 3.9 is kind of like getting over the hump in chapter 3 as far as defining the derivatives goes. Sections 3.10, 3.11 will be slightly lighter material. But any questions at all before we jump back into section 3.9? Okay, well, let's get started. Here's where we left off last time. We ran into like the last minute of class and just briefly took a peek at this one. Oh, great question about that. Thanks for asking, Logan. I don't have any late homework policy whatsoever. And so from any section that you might be past due, if you just turn it in normally through the system in Canvas or email it to me, I'll accept it at full credit. Other questions at the moment? Yep, absolutely. Thanks for asking about that. I'll probably make that an announcement when I send an announcement out for just reminding to schedule the exam. But let's get started then in our section 3.9. Here's where we left off. We're looking into a famous law from physics, Boyle's law. It says, when a sample of gas is compressed at a constant temperature, so we have a constant temperature, the pressure and volume satisfy this equation. Pressure times volume equals C, where C is some constant. It needs to be a constant determined for each gas in each new experimental setting. So with constant temperature, pressure and volume satisfy that relationship. If we increase the pressure because maybe volume is decreasing, you'll still always maintain that relationship there. It says next, suppose that at a certain instant in time, we have some enclosed volume, and that volume is 600 cubic centimeters. We know the pressure, maybe there's a gauge on this, maybe it's a cylinder, for example. The pressure at that instant of time is 150 kilopascals, a typical unit for pressure. And we're also told the pressure is increasing at a rate of 20 kilopascals per minute. So we have something that's 600, I don't know if this is big enough to visualize, but I'm imagining 600 cubic centimeters as a volume, maybe a cylinder. The pressure is increasing must mean that the volume is decreasing. Maybe it's some kind of cylinder like in a small engine. The volume is decreasing and the pressure is increasing at that rate. So we want to know at what rate is the volume decreasing at this instant. So this is a typical problem in the section 3.9 related rates. There's lots going on, and a good strategy is just to read it once and then read it again to see if we can identify, translate into our own mathematical language what all of the moving parts are for each one of these scenarios. So looking at this again, we have an equation, pressure times volume is constant, C. So PV equals C. It says, suppose at a certain instant, let's highlight that. And it's mentioned again when it says at this instant, we're referring to some instant of time. So let's just define it. Let T naught, we've used the T naught symbol before, just one definite time value, so not a variable, some other constant. Let T naught be the time at which the following happens. Volume is 600 cubic centimeters. So referring to that variable, V equals 600 centimeters cubed. We're told next, the pressure, let's code it this way in green, comes out at 150 kilopascals. So let's write out in our notation, P equals 150 kilopascals. And the most important word that's labeled here is right where it says rate. When that word came up, we have a rate of 20 kilopascals per minute. Pressure is increasing at that rate. This information tells us that dP dt, this is at a specific instant of time, so evaluated at time equals T naught, is increasing, so it's positive, so we don't have to put a negative sign. At a rate, that's the derivative here, dP dt, 20 kilopascals per minute. The kilopascals is the unit for pressure per minute. The minute is the unit for time, the bottom part of the Leibniz notation derivative. So that's all of the given information. And now comes the question. The question is, at what rate is the volume decreasing at this instant? So we're being told, find dV dt, evaluate at that instant of time, T equals T naught. Let's put a little question mark there to say, once we put a number down to that, our work is completely done. We're expecting negative because the only way pressure is increasing is if the volume is decreasing. The gas is being compressed with a decreasing volume. So the rate of change with volume with respect to time, all I can say for sure is it's definitely negative in this problem. So this is all the given information, and this is a good strategy as well. So I would say first step, just read the problem. Second step, after you have that visualization in your head, start writing down information. Put down everything that that problem indicates as a given value. You know, we could have also said this part, C is constant, that's important too. C is constant. Then once we have everything written down in our notation, we do step 3, start working the calculus. We want the rate of change of volume, which means we need to differentiate that equation, and we want it with respect to time. So let's indicate it this way. Our first step, take ddt of P times V equals ddt, just the derivative with respect to time, of the constant C on the right-hand side. This step in the middle could be skipped, but it's just a good note-taking way of saying what line comes right next is the result of taking this derivative right here. So we're just about to get started. Any questions whatsoever before we differentiate? Okay, a couple observations we should make, however, is volume, it depends on time. Pressure also depends on time. These are functions of a new variable, T itself. So P, we can say is a function of time, V is some other function, let's call it G, of time. So when we go to differentiate this, we're taking a derivative with respect to t, which means this is implicit differentiation altogether. There's a real function there for p, we just don't know what it is. And since this is a product of two functions altogether, this requires product rule. So let's write out the product rule for p times v. The typical way we've done this is we took the derivative of p first and then copied v. Because it's in Leibniz notation, I'd probably write it in this order: v times the derivative of p, which we're writing in as dp dt. So here's the derivative of p, v copied in. It's a product rule, so we go plus. Now we're copying p down. We're taking the derivative of v, so this becomes dv dt. Equals, on the right, the derivative of c. Because it's a constant, we get to use the constant rule on that one. It comes out as 0. So now the derivative is done, and our goal is to solve that equation there. So we can solve for that derivative, plug in all the information for the values that we've indicated up above, the value of this derivative dp dt as well, and then our work is going to be complete. So this is the major step, getting right to this spot here after taking the derivative. Any questions or thoughts getting to this stage? Okay, well, let's start solving for the derivative, dv dt. Since we want to evaluate it at a time, that's the unknown in the problem. We can subtract off that whole derivative there times v. So p times dv dt equals negative v times dp dt. Last thing we can do here is just divide by p. So dv dt equals negative v divided by p times dp dt. And at this stage, we're in a really good position. We just need to evaluate this at time t equals t naught. The derivative is being completely isolated for. So here's our final step. This means dv dt evaluate at a specific time, t equals t naught. This is the derivative at any moment of time, but we knew at the instant of time t naught, a whole bunch of stuff happens. We know the volume, we know the pressure, and we know the rate at which the pressure is changing. It's increasing at 20 kilopascals per minute. So we can plug everything in the right-hand side, and here's what we get. This is now equal to negative volume of 600 cubic centimeters divided by a pressure of, let me get that color in, 150 kilopascals. Then it's multiplied by the derivative, dp dt. We have the value for that one as well. dp dt is 20 kilopascals per minute, so I'll go times 20 kilopascals per the minute. And this is the rate at which volume is decreasing, and we see decreasing due to the negative sign. So we have some internal consistency there. It should be in units of cubic centimeters per minute. But we're there because in the unit analysis, the pressure unit cancels out, and we do have cubic centimeters per the minute. We just need to multiply through all these numbers. So let's pull out the handy calculator. This is a good reminder for exam 2, exam 3, and the final exam. You're allowed a scientific calculator just for these kinds of things. 600 times 20 divided by 150 would give us altogether negative 80. So this becomes equal to negative 80 cubic centimeters per minute. So that's the rate at which volume is changing at that specific instant of time. If it continues to compress, if the pressure continues to increase, maybe the rate of change for the volume is going to change as well. And so this is only valid for one particular instant. But this is the process of taking down a formula like this, Boyle's law, famous equation of physics, and applying calculus to it. It's related rates because the relationship is volume and pressure. I said that backwards. Volume here and pressure here are all related by an unknown variable, or excuse me, a new variable t, and two other unknown functions. So any questions at all, folks, with the conclusion for this? Okay, well, for the next problems, we're going to look into something a little bit more spatial. The next example, we're going to look into just kind of a strange scenario. Two people starting from the same point, one's going east, another going south. We want to know how fast is the distance changing between the two of them. Then we're going to extend this kind of idea, loop in the law of cosines, and look into how fast is the connecting rod, or excuse me, the piston here moving at a specific instant of time when the angle is at pi over 3. So we'll look into a little bit of mechanical engineering in this kind of scenario. So first, this one's kind of like the warm-up before we get into the next example. It's a complicated situation. Usually in, say, an algebra class, you talk about maybe two people starting at a common point, walking in opposite directions. That walking in opposite directions part of the problem actually simplifies the math a good deal. But this one, they're walking at different angles, a 90-degree angle from each other. And this adds a bit of a complication layer to this, making the work a little bit more tricky to get through. It says two people start from the same point. Let's draw a diagram to go along with this because it's a pretty visual problem. Here's their common point where they're going to start. Maybe they had an argument, so now they're just moving away from each other. One person going east at the rate 3 miles per hour. So here's the eastward person. I'll call this distance x. And we have a derivative for that dx dt equals 3 miles per hour. So the other person involved here is going due south at 2 miles per hour. Not quite as fast, maybe not quite as upset after maybe this was an argument that separated them. So here's the person, I'll call that distance from their common point, y, and we know the derivative dy dt equals 2 miles per hour. So we're assuming that they make no change in their walking. They're going to keep that gait exactly 3 miles per hour. This person gait exactly 2 miles per hour. So kind of an idealized situation. The question is now, how fast is the distance between these two people changing after 2 hours? So if we want the distance between them, we can say go from this point to this point. We have another line segment going this way. We can call it z just because that goes along with xy. If we can find this length right here, we'll be talking about distance. So we're concerned about that distance there. But notice the way the question is phrased. The question is phrased in the terms of how fast. Fast here means we're talking about a derivative. And so we want to find out. We want to find dz dt, and specifically that rate of change of distance with respect to time when time equals 2 hours. If we can find the value of this derivative right here, our work is done. So we have two known derivatives, dx dt, dy dt, coming from this piece of information, which involves the x and y variables. But now we have a common issue that's going on, just like on the first example in these notes. X is some function of time. Y is some other function of time, and Z is yet another function of time. I'll go with H of t. We might be able to find some of those functions. This one would be the tricky one to find, but the easier approach is just using that information, we can differentiate implicitly, like we practice on these notes as well as section 3.5, and solve this problem in a pretty reasonably quick way. So here's the setup to all of our information so far. And the fundamental relationship that's going to allow us to relate variables x, y, and z all together is Pythagorean's theorem. Because we have someone going due east, another person going completely south, that's a 90-degree triangle we're really looking at. So Pythagoras has something to say about this. Pythagorean's theorem says, let me get my colors loaded up, z squared is going to be equal to x squared plus y squared. So that's Pythagorean's theorem altogether. Now we have a relationship, and we can differentiate this with respect to time, because that's the derivative we want to determine, dz dt, at 2 hours. So we take the derivative of the left-hand side, d dt of z squared, take the derivative of the entire right-hand side, d dt of x squared plus y squared, and from here, we're kind of on our way. But this is where it gets challenging because it's not a standard derivative. This is not d dz. If that was d dz, that would just be 2z, and the whole story is over. Likewise, this derivative is not d dx, and if it was, it would be just a 2x, and nothing further to say. These derivatives are d dt. We have to use the fact that x, y, and z are all functions of a new variable, time itself. That implies every derivative we take here is going to involve the chain rule. The inner function is z. The outer function is the power 2 function. So following the rules for differentiating using the chain rule, we differentiate the outer function first. 2 comes down. The new power is 1. And then we multiply by a new derivative, d dt of whatever the inner function happens to be. The inner function is z, so it goes into this spot. That's really just z now, z to a power 1, not prime. And this we can just write in as dz dt. So that's the same kind of process as we did in the implicit differentiation section. The only difference now with related rates is every variable is a function of some other variable. Time is the common one. So every time we differentiate, it's a chain rule in this configuration. We'll finish off the rest of the derivative for the x squared plus y squared. But any questions at all, folks, doing the dz dt part? Okay, let's continue through the derivatives. Nice thing about this problem is the differentiation is not as hard as the last one, which involved the product rule. In my opinion, that one is a little bit harder. This one's not so bad because if you can do it once for z squared, same process for x and y, you're just changing the name of the variable. Caleb says, so for this, we aren't solving z. That's right, for this one, we're going to be solving for dz dt. So this part right here that came out through the chain rule. Other questions at the moment? Okay, well, let's move through the last parts here to complete the derivative of both sides of the equation. Differentiating x squared, first we take the derivative of the outer function. This becomes 2x to power 1, or just 2x for short. We're just mainly emphasizing the process of the chain rule by putting in that parenthesis and a power 1 on it. Then we chain on a new derivative. It's the derivative of x with respect to time, so dx dt. Then, using the sum rule, we just move over to the next term, do that next derivative. It's 2 times the derivative excuse me, 2 times y to the power 1 times the derivative dy dt. And we have some nice knowns here. We know dx dt is 3 miles per hour. We can plug that in here. We know dy dt is 2 miles per hour. We can plug it in here. What we don't know is the value for x, y, and z. But we can find those. The key to that is we're really only interested in the value of the derivative at time 2 hours specifically. So we can make a new diagram and say, this is what the situation looks like at the 2-hour mark. But maybe before we do that, notice one nice simplification you can take just right now. You can take this whole equation and just divide it by 2. Not fully required, but if you can drop the complexity of the equation even by a little, it's well worth it. Let's put down the simplified equation. Z times dz dt is now equal to x times dx dt plus y times dy dt. Now, we have this diagram to start, but this diagram is for any time t whatsoever. So now we're going to say at time t equals 2 hours, the 2-hour mark is of particular interest, this diagram turns into this. It'll still look about the same proportionally. Maybe instead of arrowheads, let's make it look a little bit more static. Person is at that spot in 2 hours. Person going south is at that spot in 2 hours. Now for the x variable, if they were going at a rate of 3 miles per hour, then in 2 hours, this would be x equals 6 miles. Likewise, at the rate of 2 miles per hour, if you travel that rate for 2 hours, this would be y equals 4 miles. And still don't know the z part. We need to cite Pythagoras' theorem one more time, but that's really fast now. In this diagram for z, let's leave a blank there. We can still say z squared equals x squared plus y squared. So z squared becomes equal to the square of x is 36, plus the square of y is 16. So altogether, z squared is equal to 46, 52. And 52 is 4 times 13, I believe. 40, 12, carry the 1. Yeah, it looks like 52. So when you go to take the square root of this equation, you get z equals, you can square root the 4 for a 2, multiply by square root 13. So now we have a value for z, a value for x, a value for y. We have the values for dx, dy here and here. We can plug in everything, and the only unknown will be that at time 2 hours. So that's going to be our next step. Any questions at all, folks, before we go to drop in all the information down here? Okay, let's make this substitution happen. First, for variable z, we see on the right, it's 2 root 13. Because I put in a number for z, we should renotate this. This is not the derivative of z at any time. This is the derivative at specifically 2 hours. So we should rewrite it this way, just to be completely literal about what that derivative has turned into. It's an evaluation at time t equals 2 hours. It's going to be equal to, we have a value for x to the right, it's 6 miles per hour. dx dt, excuse me, just 6 miles, and then dx dt is 3 miles per hour. So it's going to be times 3 plus, next value for y is 4 miles times the rate of change of the y variable with respect to time, 2 miles per hour. I'll go times 2 here. And the moment we just proceed with this equation, solving for the dz/dt portion, our work is completely done. So now it's all just algebra from this part on. So that's a substitution step. Next step, we have dz/dt at t equals 2 hours is going to be equal to, altogether, I'll divide by that 2 root 13 into the right-hand side. The right-hand side numerator is 18 plus 8, which becomes a 26 over 2 root 13, which becomes a 13 over root 13. And that's a pretty good stopping point. But just for the sake of reviewing just a little bit more algebra, I think rationalizing the denominator kind of makes sense in this one case. It looks like a real simplification. You can multiply by the root 13 over the root 13. Again, this is an optional step. Numerator is 13 root 13. Denominator is 13. And so you get just altogether square root 13 in units of miles per hour. And so that's the full story of this one, how the distance is changing. This is the distance at any time, t represented here. We never solved for that dz/dt. We plugged in the information, filled it out. But now we know if one person is moving to the right at 3 miles per hour, one person is moving down at 2 miles per hour, the distance between them, specifically at the time, the 2-hour mark specifically, is changing at a rate of square root 13 miles per hour, increasing at that rate. So that's how far apart they're getting at the 2-hour mark. Well, kind of a different kind of related rates problem. Any questions or comments at all, folks, running through this whole scenario here? Okay, again, it's a pretty big extension to problems that have been studied before in algebra. It just simplified a lot because Pythagorean's theorem allowed us to, through the 90-degree angle here at pi over 2, just drop down to that equation really fast. So other questions you might have is, what if these two people started at the same common point, but they didn't move in directions that are perpendicular to each other? Maybe they moved in a way that one person and the other had an angle measurement between them at, say, pi over 4 or maybe pi over 6, anything like that. If that happens, Pythagorean's theorem is off the table, and so we can extend this problem into using law of cosines and still solve it. That's kind of the theme of what's going on with the next problem, but also different context, more about mechanical engineering with what's going on in the next one. Good review of trigonometry at the same time. So think of this problem, which is kind of weird and vague and silly, really just being sort of a warm-up for the next problem down below. It's going to involve law of cosines, so we'll study both these elements. This to review from pre-calculus 2 to start. Let's look at this situation first to see what's going on with this new context that even requires law of cosines. Let me see if I can blow this all up a little bit more. That's a great question, Caleb. I would say if law of sines or law of cosines comes up, I'll definitely include this on a real exam. I think this is getting to the point where not really just common trigonometry like function evaluations and such. This is more the kind of equations where people do use a lot, but they're easy to forget. You can go long stretches, years even, before you use this equation out in the wild, like in this problem below. So anything that's kind of a more less used equation like this, I would put on an exam situation. You're not expected to remember 100% of pre-calculus 2 trigonometry. Other questions at the moment? Okay, let's check out this diagram below. It says, in the engine showed in the figure below, a 7-inch connecting rod is fastened to a crank of radius 3 inches. And already it's kind of a lot of busy information here. I've never really studied engines in high school or college, so this is a lot of information for me. We have the piston, spark plug, which caused an explosion, shoving the piston to the left, but in a controlled way. This is the connecting rod right here. And this little line doesn't really have a great arrowhead to convey it. Probably didn't want to make the diagram too busy, but that's the connecting rod at 7 inches. The crankshaft, this one is at 3 inches. And this line segment, well, it's going to change. It's a very dynamic picture. The piston is either moving to the left at a certain rate of speed, and then that line segment there on the horizontal gets smaller, or it's moving to the right at a certain rate of speed and it's getting longer. And the rates of speed change quite a lot. So that's the layout of the land so far. It says next, the crankshaft rotates counterclockwise at a constant rate of 200 revolutions per minute. So this sounds like an engine at idle. It's a well-tuned engine, so that rate is literally constant. It's going counterclockwise, so it's going like that. So imagine a movie of the piston moving to the left and to the right, the crankshaft and the connecting rod, rigid structures, they're just rotating along with this. It says, find the velocity of the piston. So how fast is it moving and in what direction when theta is pi over 3. And theta is that internal angle right there. If it were pi over 2, that would be a 90-degree angle. And we can really just redo all the work we did on the last problem. It's not people moving from one spot to the other, but there's lots of similar elements. Because the angle is pi over 3, this is where we really need the law of cosines. So law of cosines essentially says, if your angles go alpha, beta, gamma, and the opposite angles are A, B, C, then you have these 3 different equations. They look almost just like Pythagorean's theorem, but if the angle is not pi over 2, you need that value right there. If alpha is pi over 2, cosine of pi over 2 is 0, and you just get Pythagorean's theorem back. So a great way to think about this one is kind of matching where our angle theta is. Let's focus on alpha in this diagram. If alpha is here, we go to the opposite side, A, and we square it. Then we look at the angles adjacent to alpha, C and B. We sum their squares. A squared is equal to C squared plus B squared. That looks like Pythagorean's theorem, but then law of cosine says the true measurement here for A squared is take away 2 times C times B again, times cosine of that angle alpha. So we'll do it again down below here, but that's the big punchline. It works for any one of the angles you decide to measure. I focus on alpha just because our theta seems to be in the position of alpha in a diagram above. So what's going on with this? We're going to use the law of cosines as we see here on this diagram. Any questions or thoughts at the moment? Okay, let me just take a quick screenshot here so we can scroll down. Now here's the next really important strategy for a problem particularly like this one. This is a really busy diagram, and so anything we can do to simplify this is extremely worth it. So that's what we're going to do next. Caleb says, so this isn't the rate when the piston is moving. It is the rate for the piston as it's moving, yes. So the whole diagram is moving, and we're saying right when the piston angle here, right when the angle here between the horizontal and the crankshaft is pi over 3, we want to know how fast it's moving and in what direction. So it is about the rate when the piston is moving on this one. Does that make sense for that question there? Any other questions at the moment? Okay. Well, here's the next thing we should try for this diagram. Loft cosines is a little bit easier to analyze on the diagram below because it's not such a busy diagram. The diagram that we have above, there's just really too much going on. So one of our major tools for handling a situation like this is abstraction. The major element is that triangle that's kind of indicated with the red line segments. So let's just redraw that. Let's use red again to kind of indicate where it came from. We are going from here to here, way out here. There's a horizontal piece going this way. So there's our triangle from above. It's a cleaner diagram now, so it's just a little bit easier for us to analyze if our eyes are looking at this. We're focusing on just the tree, not the whole forest of what's going on in this engine diagram. Now let's bring in some information. There's a 7-inch connecting rod. That's this piece right here. So let's call this 7 inches. There is a crank of radius 3 inches. This is the crank right here, or crankshaft. So 3 inches going this way. And let's see, we want to find the velocity of the piston when theta is pi over 3. So that's this dot right here. That dot is moving to the left. It's moving to the right. So we're very concerned about this right here, the length of this segment. We can give it a variable name, say x should do the job. And what we're very curious about is then, what is the rate of change of x? Is it positive? Is it negative? Specifically when the measurement here for theta is pi over 3. So here's all that information copied down below into this diagram. Everything except for the question, well, it's less of a question, more of a demand. Find the velocity of the piston when theta is pi over 3. So let's write down what the question is of the problem, the implied question. We need to find the velocity of the piston is how fast it moves, if it's moving to the left or to the right. But we can convey that information just in terms of how fast is x changing, the distance between here to here. So we can call this dx dt. So we want to know what is dx dt specifically at the value theta equals pi over 3 equal to. We can find that value, our work is entirely complete. So now we know the implied question. We have a lot of information in this diagram here. And this is a good point to just reread the question. One element of good question writing, like what comes in the textbook, that I proofread the exams to make sure happens as well, is every piece of information in these problems is really necessary. So another nice strategy about these problems is, if you notice there's one piece of information we never used, take a closer look at it because it's probably really important. So we have a 7-inch connecting rod, crank of radius 3. But here's something interesting. Crankshaft rotates counterclockwise at a constant rate of 200 revolutions per minute. We've never actually used that piece of information yet in this problem. We were talking about how fast is this distance changing, increasing or decreasing, which corresponds to the piston moving to the left and the right at a particular angle. But we never use that. So let's bring in that information there and then proceed to the next part. So if it's going in the clockwise direction in angles measured in standard position, that's a positive angle. But it says rate as well. So it's talking about a derivative of the angle. So this is saying d theta, the rate of change of this angle right here, or here in the larger diagram, with respect to time, this derivative is a constant derivative, and its value is 200 revolutions per minute. Let's add one other piece of review information from trigonometry. 1 full revolution is 2 pi radians. I'll write rad for short. Oftentimes in a trigonometry course, pre-calculus 2, we drop the unit rad, but I'll bring it in just to emphasize that's the measurement, just the angle itself. So if this crankshaft, it's going rather fast, but it's an engine, if it's doing 200 revolutions per minute, we can say that that's 200 full revolutions per the minute. A single revolution is 2 pi. So we take 200 times 2 pi radians per minute, which means it's 400 pi radians per the minute. So this information here, it gave us a derivative. It's just kind of disguised in the problem. That's where the words like rate become such a big buzzword in the writings of these problems. So always look for something like that. Instantaneous rate or the constant rate, anything like that is talking about a derivative, really. So at this stage, we have pulled in all the information. We want to find dx dt. We have a diagram that involves x and it involves theta. So that information is here. And this makes it a related rates problem. We can relate to the rates of theta, d theta dt, and x, dx dt themselves. The equation that ties them together is the law of cosines that's copied down here for that problem, for that diagram below. Okay, we're ready for law of cosines. A lot of these problems take a good amount of analysis just to get started, pull in the information from the diagram or from the words provided, like on our first example, 2 for the day. Any last questions or thoughts, folks, before we move beyond the diagram? Okay, well, again, let's hit this with law of cosines. Copying this diagram down, whatever values you put down, it's less about the alpha, beta, gamma, the A, B, C, and more about just the pattern. We go from an angle to its opposite side. We take that opposite side and we square it. Here, the only angle provided is theta, so we go to the opposite side of that angle theta here, which is 7 inches, and we square that. So it begins with the 7 squared equals. Then we take the adjacent sides to the angle, sum them and square them. The adjacent sides are 3 inches, so go 3 squared plus x squared. Here's where x occurs. Because this is not a 90-degree measurement, it's not pi over 2, we put in the law of cosines extra portion here, the corrective factor. But notice this pattern. If you went c squared b squared, it's minus 2c times b. So here we'll go minus 2, just a 3 times the x, following that same exact pattern. So x comes in again, and then we go times cosine theta for this problem. So that's the use of the law of cosines. Now that we have this, much like on the very last example, our next task is to, let's simplify the equation a little bit first, then we'll differentiate it. Well, any questions at all, folks, with law of cosines? Okay, let's move on to the next part. There's not a whole lot we could do to simplify, but there's lots going on. So any way you can make it just a little bit nicer to look at is well worth it. We can rewrite this as 49 equals 9 plus x squared minus 6x cosine theta. Subtract 9 for both sides, and now we have 40 equals x squared minus 6x cosine theta. Hide this for the moment, still available up above on the notes. Now our next task is to differentiate both sides of this equation, but the derivative we're taking is respect to time. That's the provided derivative d theta dt. And more critically, we're taking a derivative with respect to time. because that's the question. What's dx dt at a specific value? So we can say on the next line, we're taking d dt of 40 equals d dt of x squared minus 6x cosine theta. But we need to be really cautious with this derivative, just like on all the other problems in these notes. X is a function of time. Theta is also a function of time. The derivatives provided here, asked here and provide here hint at that. So when we differentiate things, like say the x squared, that's a chain rule. When we differentiate 6x times cosine theta, that's a product rule on this one. Let's highlight that in yellow. I'll carry the sign as well, why not? So we have to use the product rule here. And even more, when we say see cosine theta, this is going to involve the chain rule. So let's carefully run through this derivative. On the left-hand side, maybe instead of trying to squeeze it in, let's say the derivative is just going to continue on to the next page. So let's say here, continues. The next derivative is the derivative of the constant, 40. That derivative goes to 0. Then over here, using our skills of differentiating implicitly, much like in the last problem, if we differentiate x squared with respect to x, that's just 2x. But if we differentiate it with respect to time, and x is a function of time, this becomes 2 times x. We chain on the new derivative, dx dt. So that's the chain rule in that portion right there. Then on this portion, we need to be really careful because we're using the product rule on this side as well. So let's carefully run through the product rule on this portion. In the product rule setup, we take the derivative of the first factor, copy the second factor. I'll put cosine first when I write it in. It's going to be plus cosine theta. Next, differentiate to negative 6x. That would become negative 6 times the derivative of x. That's just going to be written in as dx dt. We don't know what x is as a function. It has not been solved on paper anywhere here on the notes. So we just call it to dx dt altogether, which is good because the question is, what is dx dt at a specific value, pi over 3? So seeing dx dt appear is great. We can isolate that, solve it, and get a value out. So this is the first part of the product rule. Then we go plus, and then now we're going to copy the first function, negative 6x, multiply by the derivative of the second function. So when we differentiate a cosine, we get a negative sign at the same angle, theta. But then we have to multiply by the derivative of the inner function. Theta itself is a function. So we chain on the derivative, d theta dt. So that's where the dx dt's come into play. And this is where d theta dt gets involved as well. So we're done with the derivative. It's kind of a mess, but we use law of cosine, so it's almost to be expected. We are trying to find dx dt. We know the value for d theta dt. We're going to plug in a value, pi over 3. So we'll know a value for theta, sine theta and cosine theta are knowns. But the one thing that we don't actually know yet is x. When theta is pi over 3 as a value, what is this distance in the first place? We do need to solve for that because it shows up on this equation in 2 spots, the 2x here and the negative 6x there. So that's our next leg of the work. Find the value of x itself on the next step. Let me put a little border here. I think we can do it on the white space to the right over there. Any questions at all, folks, before we solve for x? Okay. Well, the question is, what is the velocity when the rotation between the crankshaft arm and this horizontal is pi over 3. So we can now say at theta equals pi over 3, what we know is that equation holds at any value theta whatsoever. So let's just pull that in. When theta is pi over 3, let me just select a good color here. We're going to do a valuation, let's say at theta equals pi over 3. To get the new equation, it'll read in as 49. You know what? I'm probably should use the one down below. We simplified it, so let's put that work to good use. At that equation, after we simplified when theta was pi over 3, here's what happens with this equation. We get 40 equals x squared minus 6x times cosine at pi over 3. And in that equation right there, we can solve for x. It appears as a variable just in, well, there's only one variable in this equation is a better way to say it. It appears in two different terms. Cosine pi over 3 is just a half, so this turns into 40 equals x squared minus 6x times 1/2. So the equation simplifies to 40 equals x squared minus 3x. That's a nice equation. It's a factorable polynomial. Let's move 40 to the opposite side. 0 equals x squared minus 3x minus 40. And then upon factoring, here's what we get. X and x would go here. This should be a plus and a minus. And I would say something like plus 5 minus 8 should do the job. That means there's actually two solutions for x. These values are measured in units of inches, but x here in this diagram, it cannot be a negative value. This piston conceivably only moves to about right here, maybe not any further than that, or the whole thing mechanically is just going to get blown up, that will blow a piston, I guess you could say. So the minimum distance is a positive value. X can't be 0 either. There's a maximum distance, but the major thing is x cannot be -5. That makes no sense on this diagram. From here, we could plug in an 8. That balances the equation 0 equals 0. So that equation implies x equals 8 inches. And that provides us something new we can substitute in. We're only interested at pi over 3. And at pi over 3, we now also have a value for x at the same time. So this has turned into just one big long equation where we're just dumping everything into it for the purpose of solving dx dt. But if you look into every problem you've done on the notes, that's a theme for this section. That's pretty much how every problem went down. Find your information, use a formula or a diagram, differentiate it, maybe use another equation to get all of the unknowns on paper, and then substitute everything in. In fact, example 1 followed that same kind of flow. Well, before we start dropping in the information, any questions or comments to this stage? As far as the exam questions go, I believe for exam 2, I wrote it the other day, but I've forgotten. I think I might have it on me. Let me double check. The total number of questions on this exam came out to 10 questions altogether. So much like the other ones, it's not meant to be an exam where you're going to be writing for the entire 75 minutes. If you've gone through the homework, practiced reviewing any kind of lecture notes or the sample exam 2, available on Canvas as well, you'll be in great shape for getting through it. So you should have extra time at the very end of the exam just to double check your work. Other questions so far? Okay, and just on a similar vein, because a thought popped up on my head as well, keep in mind that exam 2 only goes up to section 3.7, the section that we finished last week as well. I didn't want to make the exam too long in terms of questions on the exam. I didn't want to make it too long in terms of sections either, so it has that cutoff in 3.7. Well, at this stage, let's start plugging in the information. We can now say at theta equals pi over 3. Here's what we're going to get in this entire equation over here. We have 0 equals 2 times 8 inches let me highlight that in orange, just show where that value came from, times dx dt, that's the unknown, so times dx dt. This is at theta equals pi over 3, plus cosine of pi over 3, times -6, times dx dt again, at theta equals pi over 3. Then just a couple more. We are currently in section 3.9, related rates. Then for the next part, go plus -6 times x again, which is 8, multiplied by d theta dt, that's our final substitution to make. But that was a derivative that was provided. This is a stable, well-running engine, so it rotated at a constant 200 revolutions per minute, which implies the rate of change of theta with respect to time is 400 pi radians per minute. So we go times 400 pi in term units of radians per minute. I'll drop the unit for the moment so it doesn't get too unwieldy. So now this is an equation for which we can solve for dx dt. So nearly there. Let's scroll a little bit further to finish this off. We have 0 equals 16 times dx dt at theta equals pi over 3, plus cosine of pi over 3, we saw before, that comes out to a half. So that's a half times -6. So it's really just -3 dx dt at theta equals pi over 3. This becomes -48 times 400. That looks like a calculator job. So hang on, let me double check this. I think I missed one thing here. I got the 6 times the x was 8. I have the d theta, here's that down below. But I neglected the sine theta. Let me plug that in. There's just so many pieces to put in, so let me not forget this all-important piece, times negative sine at pi over 3 again, then goes times 400 pi. Let me double check that substitution. Yeah, 400 pi radians per minute. So there's that missing factor right there on the last term. So this becomes altogether, we can cancel our negative signs, so it's now positive. Let's maybe still go to the calculator on this one. 6 times 8 times 400 gives us 19,200 times pi times sine pi over 3, which is square root of 3 over 2. Good a bit of algebra in the very last part, kind of similar to the rest of the problems we've done. We're nearly there. We can now isolate for dx dt, simplify this a little bit more. First two terms are like terms. You have 16 copies of the derivative minus 3 copies of the derivative means 13 copies of dx dt when theta equals pi over 3. So there's our like term. And now let's take this, divide it by 2. So 1900, 200, division by 2 is 9,600 plus 9,600 pi root 3. So just about there. This is an equation of one variable, linear. So subtract the 9,600, divide by root 13, and we get that dx dt, evaluate at theta equals pi over 3, is negative 9,600 pi root 3 divide by 13 in units of inches per minute. So step back on this problem a little bit, all the way to the original diagram. What it's saying is when theta is pi over 3, and this is moving in the clockwise direction, counterclockwise direction, so this arm is moving that way, it's dragging the piston to the left. We see the left movement with the negative sign in the derivative. That's moving to the left at that specific rate. Let's get an estimate on it. Negative 9,600 pi square root 3 13ths means it's moving negative 4,018.3 inches per minute. So in this diagram for this engine, that's how fast it's moving to the left at the moment of time when the angle is specifically right at pi over 3 radians. Definitely an adventure of the problem. It's an extension of what we did on the last one, where two people are walking, one going east, one going south, but it had a rotation element on top of it at the same time. So that's why this problem seems to get wild as well. But at its heart, it's really just law of cosines differentiated and then plugging in all of the information of the problem right on top of it. Any questions or comments at all, folks, getting through this problem here? Okay, well, it's definitely a messy problem, but this is what happens with these kind of applications. This one is quite realistic for a classroom like this one. And the more realistic the application, the closer it is to mechanical engineering, physics, chemistry, biology, medical sciences, the closer we get to anything like that, the crazier the calculus seems to get. So these kind of problems, they won't make for great exam questions. This would be an exam 3 topic. But these are the kind of problems that you'll study and solve in the homework as well. So we solve equivalently difficult ones. And in an exam setting, because exams are timed, a more reasonable problem that you would see for an exam might be example 3. That one would be pretty long. Example 2 would be just right. That one didn't explode on us. Example 1 is pretty abstract. It's just a random mathematical equation, but this one would be just about right for an exam setting as well. But it's good to solve realistic problems, even though they get messy and kind of uncomfortable when the algebra and the calculus seems to explode on us. But it's sometimes satisfying to see just how powerful all of our tools are so far. And this is just single variable calculus. Well, like we mentioned at the very start of class, we've completed section 3.9. And at the end of section 3.9, this is where everyone pretty much feels, me included, like we kind of got over the hump in chapter 3. This is kind of the peak. And for the last 2 topics, sections 310, 311, it's kind of widening down, not as intense. We're going to revisit some older topics like we saw before and extend section 3.3 or work on differentiating trigonometric functions into the hyperbolics. So let's take a look into those sections next. Here's our section 310. We'll finish this one off when we come back on our next class. But section 3.10 is kind of a nice one. It's about linear approximations and differentials. So there's 2 topics here. Differentials are something that's actually really kind of new, but the concept isn't too messy. It's something we need later on when we're all the way in chapter 5, towards the end of chapter 5. It turns out to be an important ingredient to something called integration. Integration by substitution, specifically the substitution rule, which is a way to reverse the chain rule in a certain sense. So we're introducing differentials now, but something we'll really use in earnest when we're towards the end of the class. But linear approximations, the first topic, is really something we've seen before. Let's work through the notes and then make a connection down below. So that starts off by saying, we use a tangent line to a function f at a point a f of a as an approximation to the curve y equals f of x when x is near a. Really, that's the very first topic of the course, section 2.1, the tangent problem. We had a curve that we want to approximate its slope at using the tangent line here. We eventually found out how to get that slope exactly. We just took the derivative of the function, evaluated the point right at a, and we found the slope. The tangent line was the best linear approximation to the function y equals f of x at the point a f of a. So really all we're doing is studying this topic a little bit more, extending on it just a bit. We're concerned about a point a f of a, so that makes a comeback down here below. And we know that the way to get the slope of that tangent line is, it's just the derivative. That's what's indicated here, f prime at a. Let's use the same color. So that's where the slope goes for the tangent line. We have the f of a here, the a here, and that's a tangent line equation. It just looks kind of weird in that particular format. The reason it looks so weird is, usually when we do this kind of problem, we said if y equals f of x, and we want the tangent line at a f of a, here's what the process looked like. First thing we did was we computed f prime of x. That was our step one in the process. We did that in chapter 2 towards the end. We did it repeatedly in different spots in chapter 3 as well. After we had the derivative, our next step was to evaluate m. The slope of the tangent line is just the derivative of f at the input a itself. Then the next thing we do, the reason this line feels a little bit different is we often call this a y1. Let me try again. We often call this one an x1. That's the x coordinate. And this one the y1. And our next step in this process was we built the tangent line equation. Y minus y1 equals the slope m times x minus x1. So that was the next step in our journey. So the only thing that's new right here on this line, the way they wrote it here, is y1. We're just using the function notation and calling it f at a. x1, we're just replacing a. So we can rewrite this as y equals y1 plus the slope m times x minus x1. Then finally substitute in all of our values, and it looks like this line. Y equals, in place of y1, that's really just an f of a, plus the slope m. That's just the derivative of f at a, so that's plus f prime at a times x minus the x1. Well, the x1 coordinate is the value of a right here, so we put in a minus a. And we often distributed the derivative through, we combined our like terms, simplified the equation. But if we don't know the value of the derivative, this is the form that you would stop in. So it looks kind of funny when they write it out this way, but really it's the stuff that we did towards the end of chapter 2, like we mentioned, and in various scattered places across chapter 3 as well. So we're revisiting that topic. Any questions at all, folks? Seeing the connection between that line here and the ones below? Okay, the next major idea about the tangent line equation is we called it the best local linear approximation to the original function at f at a point a f of a. And oftentimes when we plotted both the function and the tangent line, we zoomed in to the point at which the curve y equals f of x and the tangent line was indistinguishable, at least by the pixels on the monitor. So we saw how this approximation just comes to life graphically. The function f of x is approximately equal to this stuff, f of a plus the derivative of f of a times x minus a. We call that the tangent line approximation or the linear approximation of the underlying function f at that base point a. Pick a different point and you need a different linearization. The linear function, whose graph is the tangent line, is sometimes officially written out like this, L of x. And when we write it as an L of x, we call it the linearization of f at a. But really, that's just a new name for the function. Instead of calling it y, it's an important function, so we give it a name. We call it L of x. But it's nothing but the tangent line equation itself, written using function notation. So all the stuff we highlighted and tracked through in that diagram demonstration below, really it's the same exact stuff. So that's what's going on with linear approximations. Really, we're just doing the same concepts that we've done all along, and that makes it kind of a nice refresher, a nice review to start off this section 310. So first couple problems, we're just going to find the linearization L of x. The last problem, we're actually going to do one of these approximations and show how to approximate something like, say, e to the power 0.2 or square root of pi, anything along those lines, by using linearizations themselves. Well, any questions or comments at the moment, folks, with just investigating what's going on with this brand new formula below? Okay, well, let's put this to good use. Here's what our next example, I guess first example of these notes looks like. We have two different functions, a tangent and part B. Let's hide it for just a moment. Part A, degree 3 polynomial. We want to linearize this function at a value A is 2. Well, to do that kind of linearization, here's what the process was going to look like. Really, we're not doing anything different from what we've done before. Anytime we linearized an equation, we take as a first step the derivative of the function f. So f prime at x. It's kind of nice. We've seen some pretty intense derivatives, particularly in the last sections. So this one's refreshing. This just becomes 3x squared minus 2. So that's step one. On step number 2, if we're going to find the linearization, it's just a linear equation. So the next thing we need is the derivative. We need f prime at a. F prime at a, if a is a value of 2, becomes f prime at 2, which just means plug a 2 inside here. This is 3 times 2 squared minus 2. That's 4 by 3 for a 12 minus 2 for a value of 10 altogether. So we've got a slope down next. The step 3 is a little bit different because we have a new formula we're using. Our formula is that the linearization L of x is in this form, f of a plus f prime at a times x minus a. The answer is going to be in that format. So because we're using this form for writing down the linearization, my next step, step 3, would just be find f at a. So here's the a value. F at a, notice we called that f. That's the original function f above here. This is now f at 2, which becomes 2 cubed minus 2 by 2 plus 3. So this is 8 minus 4 plus 3. So that's going to be altogether 7. So that's the y-intercept of the linear function. Then finally, the linearization itself, L of x. We're calling it L of x here, just to maintain the notation. But all we're doing is plugging in this information as we have it. It'll go f of a first, which is a 7. Then we'll add in, once we're beyond f of a, the derivative of f of a, which is, we found to be a 10. So plug in 10. And then multiply that by x minus the value a, and a is 2. So that's the linearization of the original cubic function up here. And the whole problem ends right at that step. Again, it's a pretty nice refresher problem. And it's not a bad idea to graph it to see as a graphical check if we're on the right track with that so far. But you know what's kind of weird about this is that's a pretty decent stopping point. If you decided to distribute 10 inside, combine your like terms, no harm done whatsoever. But leaving in this form reveals some interesting information. That it reveals that f of a is 7 itself. That's nice to know. It's showing what all the moving parts are. Leaving the 2 right in that format tells us that the linearization happened specifically at the opposite value, a is positive 2. So if you decide to leave it in that form, no harm done. It kind of conveys a lot of information when we know we're looking at a linearization. And now for the visualization of it, let's take a look at how this compares. There's really 3 parts to the visualization. There's the function f of x, should be up here, x cubed minus 2x plus 3. We want to find the best local linear approximation to this function f at the point 2, f at 2, which is up here, the point 2, 7. So we need a linearization right at that point. The claim is that's the linearization, so throw in L of x, 7 plus 10, x minus 2, and that looks about right. We can get more numerical evidence of its correctness by seeing if we get closer and closer to 2f at 2, do the curves become essentially the same? And that looks like it really is the case for this function here. So if we're concerned about values really, really close to 2, this complicated cubic function is approximately just that. And that gives us some nice tricks and shortcuts for doing computations. Well, any questions at all, folks? Getting through this one here? Okay, let's try out another one just to see how it goes. I mean, it's on the notes too, so it'd be weird to skip it. So here's our next problem to try out. We want to linearize tangent x at a equals pi. And the reading in the textbook for section 310 gives us some good ideas on why would we want to do these kind of linearizations. Our calculators are pretty good. We can calculate tangent at pi at tangent x at a is pi, tangent at 3, for example, and so on. The reasons you might want to do these kind of linearizations is sometimes functions like these, say tangent, sine, and so on, they can get involved in complicated differential equations. And finding a solution to a differential equation is not always a very easy task or feasible whatsoever. Sometimes when people are trying to approximate a solution to a differential equation, they take in components like tangent, the problem in the example for the textbook reading is sine, and they linearize it. So as long as we're looking at solutions to that differential equation, near input value pi, the linearization can give us something that's very easy to solve, giving us a great approximation. So that's the idea so far for what linearization is all about. Calculus 2 goes beyond and tells us more of what we can do. We tack on more terms, infinitely many terms. Those are called Taylor series, Maclaurin series. And so this is also a building block into other topics later on in Calculus 2. So let's try this one out. We're linearizing tangent, saying what this is approximately like if we only care about values nearby pi. Following the step-by-step process, first thing we do is we differentiate tangent. The derivative of a tangent is just a secant squared at x. On our next step, we want the derivative not at X, but rather at A. And that's meant to be a comma. That's the world's weirdest looking comma. I should fix that. That looks a little bit better. So the derivative of f at A is just going to be f prime at pi, which is secant squared at pi. We can recall that secant is just 1 over cosine. So this is cosine squared at pi. Then, well, cosine at pi is -1. So this is just 1 over -1 squared. So the whole thing is just a 1 altogether. So the derivative of tangent at pi is exactly 1, and that's our slope. On our next step, we compute f at A, which is f at pi. This is the original function f, so we go to the very top, compute tangent at pi. Tangent at pi is sine at pi, divided by cosine pi, but sine at pi is 0, cosine pi is -1. So at pi, we get just 0 altogether. So we're ready for our conclusion. The best local linear approximation to a complicated curve like tangent nearby the base value of pi is this formula. Copying the formula laid out here, we take f of A, but that's just going to be 0. So we might simplify this one. Then we go plus. We multiply by the slope. That's the f prime at A part. We found that that's a 1 times x minus A. So we're at this portion here, but our A value is pi. So let's simplify this one, just because it's really tempting. This all just simplifies down to x minus pi. So if you're doing anything that involves the tangent function, and everything you're doing with it is nearby pi, maybe you're doing a complicated differential equation around that value, then you can treat tangent as x minus pi. That's kind of amazing because the complexity from tangent, sine divided by cosine, just the linear equation x minus pi, is gargantuan reduction of complexity. So if tangent is used in something much more complicated, system of differential equations, that simplification here to here could be what makes the difference of solving this problem whatsoever. But that's two fast linearizations down. We're going to take a look into another linearization before we move off into differentials. But any questions or comments at the moment with this one? Okay, well, the next problem down below is kind of a bigger problem. There's, depending on how you count this, really 4 parts to this one. So watch out for this one when you see it in the homework assignment for a 310. 310 has one problem that's worth 20 points. That seems like quite a lot because it's a lot going on in that problem number 6. So we're doing something very similar on this one. Let's write here just for the sake of the notes. Similar to homework problem number 6. We'll solve a very similar one here, and you'll be doing one problem number 6 in the same way. It's worth a lot of points because we're being asked to do quite a lot of stuff. We want to linearize g of x first. It's the natural log of 1 minus x at the point a is 0, so that's where the linearization is going to occur. But once we have the linearization, we're going to approximate natural log 1.05 and natural log 0.99. And it seems like a weird task because calculators are pretty good at doing this kind of stuff in the first place. But if you take a lot of programming, in particular numerical analysis, and you investigate how exactly does a calculator do natural log 1.05, one thing that's kind of amazing that you'll discover is it's doing this, but with more terms, later called a Taylor series. It's just adding up enough terms right here going to the second derivative, the third derivative, and so on, so that you get a pretty good approximation. So we're doing something that's what computer science has developed, as a fundamental thing in digital calculators for computing natural logarithms at these kind of values. So it's a different kind of application. This is more to numerical analysis, the science of computing these kind of numbers in the first place without taking out slide rules or anything else kind of archaic. But it's kind of a long problem, so I don't want to kind of rush through this one in the limited amount of time I have. This probably might take more than 10 minutes. So this will be one that we come back to when we're on our Thursday's class, the last one for the week. We'll also take a quick look at differentials. Again, differentials, they're something that become a major key in integration in chapter 5. But here's what the definition looks like. If y equals f of x, the differential is just dy equals the derivative f prime of x times dx. So we split up dy dx, we consider them as variables, and we do just a formal manipulation of these parts here, x being the independent variable. So it's a pretty short concept. We'll come back to and do 3 differentials after getting through this example right here, getting through the linearization, then the approximations. So that's what we'll have on our docket when we come back on Thursday to close out the week. But any last questions or comments at all, folks, to end class today, just a little bit earlier than normal? Okay, well, have a great night, folks. I appreciate everyone's hard work. It's particular getting through the implicit differentiation section and the last hard one, section 3.9 on related rates. If you have any questions when you're working through those homeworks, don't hesitate to reach out. I'll be happy to engage with you by email. And I'm a very quick typist, so I'm never annoyed by questions through email if you get stuck on any of those problems. But have a great night. We'll be back to this one problem here on Thursday's class. Thanks. Have a good one.